welcome to Easy BTech channel. So in this module we will see other binary codes. In the last class we have seen BCD code, which is nothing but 8421 code. So in this class we will see 2421 code, 84 minus 2 minus 1 and XS3 codes. So first we will see what is meant by self-complementing code. So a code is said to be self-complementing. If the code word 9's complement, that is how to get the 9's complement of a given number. So simply we have to subtract from 9. So if this can be obtained, that means the 9's complement of the code or the 9's complement of a given number n, if we are able to obtain by interchanging zeros and ones, zeros to ones and ones to zeros. So if we are able to obtain this or the code word 9's complement simply by interchanging zeros to ones and ones to zeros, so then such codes are called self-complementing codes, right? So when will we say it is a self-complementing code? If the code word 9's complement means we have to subtract the given number from 9. So if that we can obtain from the code word by simply interchanging zeros to ones and ones to zero. So whichever codes satisfy this property, they are called self-complementing code. So what is the advantage if the code word is a self-complementing code? So their logical complement. So changing zeros to 1 and ones to 0 is known as logical complement. Changing zeros to 1 and ones to 0 is known as logical complement. Whereas this one 9 minus n is called arithmetic complement. Arithmetic complement means, so 9 minus n is known as arithmetic complement. So we can get the logical complement or the arithmetic complement. We can get the arithmetic complement from simply logical complement. So logical complement means we simply get by changing zeros to ones and ones to zeros. So that is the advantage if a code word is a self-complementing code. So hardware requirement is less. If the code word is a self-complementing code, we can easily obtain the arithmetic complement by using the logical complement. We'll see. You can understand with the help of an example. We'll see which are the codes that are satisfying the self-complementing property, and we'll see how to get the arithmetic complement by taking the logical complement, right? So one such code is 2421 code. 2421 code. So it is also a BCD code. It is also one class of binary coded decimal, and it is also weighted codes. So 8421, 8421, and these are positive weighted coded. To be specific, they are positive weighted codes because each position having a weight which are positive. We will see in the next coming. So 84 minus 2 minus 1, in that some of the weights are negative. Whereas in 2421 and 8421 is nothing but simply we will call BCD. So it is also 2421 is also BCD, but in specific 8421 we will call it as a BCD code. So these two are positive weighted codes because each position is having a weight and that weight is a positive weight. So this 2421 code is a self-complementing code. Right? For a self-complementing code, so which codes we can, how to identify whether it is a self-complementing code is, one is by taking the nines complement of the number, we should get by changing zeros to ones and ones to zeros. So this is one way, and most of them, the if you sum all the weights, so the sum of all the weights should be 9. Sum of all the weights should be 9. So if you check 2421 code, if you sum all the weights, 2 plus 4 6, 6 plus 2 8, 8 plus 1 9. So in general, the sum of weights of all the positions is 9, then mostly all of them are self-complementing code. All of them are self-complementing code, right? So another point that we have to be careful here is, because here in 2421 code, we are having two positions having the same weight. Two positions are having the same weight. That means this position and this position are having the same weight. So that's why there are two possible bit patterns. There are possible bit patterns that could be used to represent some decimal digits. But only one of those patterns are actually used. Only one pattern is used. For example, if you take to represent 1 in 2421 code, 1 we will represent with 0 0 1. So this is the representation for decimal digit 1. So next, if you take 2, if you take the decimal digit 2, so you may think, because two positions are having the same weight, this is also having weight 2 and this position also having weight 2, but we will use only this representation for representing the decimal digit 2. So the other possible representation for decimal digit 2 is 1000, but this representation is not used. Only this representation is used to represent the decimal digit 2. This representation is not used, right? So that is why you have to be careful which representation is used. You should be aware which representation is used. Otherwise, you will end up in wrong way of doing or wrong way of representing the given decimal number, right? So in the next slide, we will see how to represent the various decimal digits by using 2421 code. So it is also one type of binary code. So it is comes under the classification of positive weighted code. It is a self-complementing code because we can obtain the arithmetic complement by simply from the logical complement, right? So these are the representation of decimal digits 0 to 9 in 2421. So 0 is represented with all zeros and 1 represented with 0 0 0 1. 2, as we have mentioned, there are two possible representation, but the representation, valid representation is 0 0 1 0. Again, for 3, so this is the valid representation 0 0 1 1, right? Another possible representation that you can do, but that is a not valid combination. So this way also, if you add the weights, so this also you will get 3, but this representation is not used. Similarly, for 4, this is the valid representation 0 1 00. So the other possible combination to represent 4 is 1010, but this is also not a valid representation. So this is the valid representation, right? And 5, for 5, this is the representation that is used 1011. So this is a valid representation. There is another representation that is 0101. So but this is also not valid. So for 6, this is the valid representation that is used 1100. So but you can have another representation also, but that is not used 0110. This is not used. This is the another representation. So in this way, there are, for every code there are multiple combination, but for 7, This is the 1, 1, 1, 0, 1, 1, 1, 0, 1. For 8, this is the representation double 1, 1, 0, and for 9, all ones. So if we use this representation only, then only it will satisfy the self complementing property. Self complementing property. So for example, here we will see why it is called self complementing property. So for example, if you take 1 decimal digit 1, the corresponding 9's complement, what is the corresponding 9's complement? 9 minus 1 is 8. 9 minus 1 is 8. So if you find the 9's complement of 1 is 8. So that we can obtain by taking or interchanging zeros to 1 and ones to 0. So for 1, this is 0001. So if you take the logical complement, so what we have to do? We have to simply interchange zeros to 1. So 1, 1, 0. So this is the logical complement of this. So which is nothing but 8. So you see, so this is a representation of 8, 1110. So whenever we get the arithmetic complement by simply logical complement, so such codes are called self-complementing codes. For any example you can take, for example, any code you take. So if you take the 9's complement of 4, what is the 9's complement of 4? So 9 minus 4, that means 5. So this is the arithmetic complement. So that we can obtain by simply interchanging zeros to 1. So here we have 0, 1, 00. So if you take the logical complement of this, what is this? 1, 0, 1, 1. So which is same as the representation of 5. So the arithmetic complement we can obtain by simply logical complement. So such codes are self-complementing codes, right? Is it clear? So this is an example of a positive weighted code, and it is also a self-complementing code because the arithmetic complement we can obtain by logical complement. So such codes are called self-complementing codes, right? So another code that we are looking at is 84 minus 2 minus 1. So it is also a weighted code, but negative weighted code, because these two positions are having negative weights, So 84 minus 2 minus 1 is an example of negative weighted codes because some of the weights are negative, right? So it is an example, and it is also having positive weights also. So it is an example of a code which is having both positive and negative weights, right? So the representation for this, it is also a self-complementing code. It is also an example of self-complementing code because if you sum the weights, so 8 plus 4 minus 2 minus 1. So this will give 9. So it is also an example of a self-complementing code. So this is how we will represent the various decimal digits from 0 to 0. Anyway, it is all zeros. So 1 is represented, or 1 we will get if you sum these positions. 8 is 0, right? So 4 is 1. So 4, and this is minus 2, and this is minus 1. So 4 minus 3 is 1. 2, we will get the representation for 2 by adding these two positions. So that is why, so this position is 4 and this position is -2, so 4 minus 2 will get 2. So 0 1 1 0 is the representation for decimal digit 2 in 8 4 minus 2 minus 1. So 3 we will get if we add the weights 4 and -1. So 4 minus 1 we will get 3, and for 4 it is simply this position is 1 and the remaining are 0, right? And for 5, so what we are doing, 8 minus 2 minus 1, so 8 minus 3 is 5. So this is the representation for 5, 1 0 1 1. For 6 what we are doing, we are keeping 1 in the 8 position and 1 in the -2 position, because 8 minus 2 is 6. And for 7 we are keeping the MSP and LSP as ones, because 8 minus 1 is 7. For 8 anyway it is simple, straightforward. The MSB we are keeping 1 and the remaining are 0, so simply it is gives 8. For 9, so we are keeping all ones, because 8 minus 4 8 plus 4 and -2 minus 1 will give you 9, right? So we have said this is also an example of a 8 4 minus 2 minus 1 is also self-complementing code. You can cross check, self-complementing code, because the 9's complement of 1. What is 9's complement of 1? It is 9 minus 1, which is nothing but 8. So if you take the logical complement of representation of 1, logical complement of representation of 1. So what is logical complement? Simply interchange zeros to 1 and ones to 0. 1 triple 0, 1 triple 0. You see, the representation for 8 is 1 triple 0. So this is also 8 4 minus 2 minus 1 code is also self-complementing code, and you can cross check the sum of all the weights. The sum of all the weights in this code is also 9. So 8 4 minus 2 minus 1 code is a example of negative weights code, and it is also self-complementing code, right? So the next code that we are looking at is XS3 code. XS3 code. So it is a modified form of BCD code. It is a modified form of BCD code. And why it is called XS3 code means, so the code word for the decimal digits, we are obtaining by adding 3 to each respect to BCD code. In XS3 code, how we are getting the decimal digits? By adding 3 to the BCD digits. So each decimal digits are excess of 3, in excess of 3 when compared to BCD, in excess of 3 when compared to BCD. So that is why this is also called as XS3 code. And another important thing is, it is not a weighted code. It is not a weighted code. So because we are not having individual positions, are not having any weights, individual positions, individual positions, we are not assigning any weights. So this is a non-weighted code. It is comes under non-weighted code. So whatever codes we have seen till now, they are weighted codes. So this example of a non-weighted code, we are getting the representation of decimal digits. So by simply adding 3 to the corresponding BCD representation. But this also satisfies the self-complementing property. This is also satisfying the self-complementing property. We'll look at the how to get the decimal digits from the BCD. So how to get means, so as we have said, we have to add 3. for each BCD. So this is the BCD representation. This is the BCD representation. For each BCD representation of the decimal digits 0 to 9, we have to add 3. So if we add 3 to the corresponding decimal digit, we will get the corresponding XS3 code representation. You can cross check any decimal digit in XS3 we can obtain by adding 3 to the corresponding decimal code. For example, you take 4. You take 4. For 4 in BCD it is represented as 0, 1, 0, 0, 0, 1, 0, 0. Now we will add 3, 0, 0, 1, 1. So then it is 1, 1, 1, 0. There was a mistake. 7. This is right. 0, 1, 1. This is right. 1, 0, 1, 0, 0. This is also right. So next 2. 2 plus 3. This is also right. 5. And 3 plus 3. So 4. So this is also correct. 4. So here, sorry, here it has to be 1. Here it is has to be. So if we add 4, this is a representation of 4. So if we add, so this has to be 0, 111. For 5, it is 0, 101. So if we add 3, 0, 0, 1, 1. So if we add 1 plus 1, so sum 0, carry 1, again 1 plus 1, sum 0, carry 1, again 1 plus 1, sum 0, carry 1. So 1, 000, 1, 000. So this is 1, 000. Sorry, there was a mistake here. So 1, 000. So this one has to be careful. So next, for representation of 6, so BCD representation is 0, 1, 1, 0. Now we have to add 3, 0, 0, 1, 1. So if we add, so it is 1, 1 plus 1, sum 0, carry 1, again 1 plus 1, sum 0, carry 1. So 1, 0, 0, 1. So there was a mistake while copying. So the corresponding representation for 6 in XS3 code is 1, 0, 1. Next for 7, the representation in BCD is 0, 111. So if we add 3 to it, 0, 0, 1, 1, right? So 1 plus 1, sum 0, 1 plus 1, sum 0, carry 1. Again, if we add 3 ones, we will get sum 1, carry 1. So again, if you add 2 ones, sum 0, carry 1. So 1, 0, 1, 0. So here it has to come. For 7, the representation is 1, 0, 1, 0. Next for 8, sorry for the mistake. For the 8, again we have to add. For 8, again we have to add 3. We have to add 3. For 9 also, to get the corresponding XS3 code, we have to add 3. I am writing the XS3 codes here on the rightmost side. So for 8, the corresponding BCD representation is 1, 000. So if we add 3, 0, 0, 1, 1. So 1, 1, 0, 1. So this one is correct. 1, 0, 1, 1. For 9, so the corresponding representation is 1, 0, 0, 1. BCD representation is 1, 0, 0, 1. So if we add 3, 0, 0, 1, 1. So if 1 plus 1, sum 0, carry 1. Again, if you add 1 plus 1, sum 0, carry 1. So 1, 1, 0, 0. This is correct. So in between 4 codes are written wrongly. So 4 corresponding representation is 0, 111. 5 corresponding representation is 1, 000. 6 corresponding XS3 code representation is 1, 001. 7 corresponding representation is 1, 0, 1, 0. So this is how to get the decimal digit representation in XS3 code. So here also you can cross check whether it is satisfying the self-complementing property or not. You can cross check whether it is satisfying the self-complementing property or not. So simply by if you find the arithmetic complement, the corresponding logical complement also should give the same answer. So that also will cross check whether it is giving correctly or not. So for example, if you take 1, the ninth complement is 9 minus 1, 8. So ninth complement of 1 is 8. So if you take the logical complement, so interchange zeros to 1. So 1, 0, 1, 1. You see? So the corresponding representation for 8 is 1, 0, 1, 1. So that is why XS3 code is also self-complementing self-complementing code, because the arithmetic complement we can get by simply the logical complement. So that is why the XS3 code is also known as the self-complementing code. So you can represent any decimal number in the same way. So for example, here it is given 395. So first we will represent 395 in BCD. So for 3, the corresponding BCD, it is nothing but 8421. So 0, 0, 1, 1, right? 9 is 1, 0, 0, 1. For 5 it is, right, 0, 1, 0, 1. How to get the XS3 code? XS3 code. So first we will represent 395 in BCD. 395 in BCD, if you represent, it is 0, 0, 1, 1, right? And then 1, 0, 0, 1 and 0, 1, 0, 1. Now add 3 to each decimal, each BCD. So 0, 0, 1, 1, 0, 0, 1, 1. So add 3 to each respective BCD number. So if you add 1 plus 1, so sum 0, carry 1. Again if you add 1 plus 1, sum 0, carry 1. Again if you add 1 plus 1, sum 0, carry 1. So this is 1. Right? Again add 1 plus 1, sum 0, carry 1. Again add 1 plus 1, sum 0, carry 1. So if you add these, you will get 1. So here 1 plus 0, it is 1. Now again add 1 plus 1, sum 0, carry 1. So if you add 3 ones, so sum 1, carry 1. So here if you add, you will get 1, 0. So decimal number 395. So this is the corresponding representation in XS3 code. This is the corresponding representation in XS3 code. So first we have to represent each decimal digit in BCD, and then we have to add 3 to each BCD digit. So we will get the corresponding XS3 code. So this is how to represent any decimal number in XS3 code, right? So this is the summary of so far what we have seen, the different binary codes: 8421, 2421, XS3, 84, -2, -1, right? So XS3, so in this XS3 is a non-weighted code. It is a non-weighted code. It is non-weighted code, and whereas 8421 and 2421 are positive weighted codes. And 84 -2 -1 is a negative weighted code, because some of the weights are negative weighted code, and out of this, these three are self-complementing code. 8421 is not a self-complementing code. Only 2421 XS3 84 -2 -1 is a self-complementing code. So I will stop here. In the next module, we will see one of the important and most practically used code, that is nothing but gray code. So thank you for watching. I request everyone to subscribe Easy BTech channel. Thank you everyone.